So next day, final day, we are going to look at your ChemCatalyst now. All right, we're practicing those drawings again, so hopefully you've been doing okay with them, either looking at your book, helping each other, or watching the videos. All right, so take a second, copy down the ChemCatalyst. You're doing all three parts, so do the electron transfer, the ionic compound formation, and write the chemical formula just like you did in your homework, and just like you will do on your first mini quiz when I get back. Okay, so you have two sets, sodium and sulfur, and then calcium and nitrogen. Pause the video while you work on those, and then you can check your answers afterwards. All right, for sodium and sulfur, you should have started with sodium having 1 valence electron and sulfur starting out with 6 valence electrons. All right, and so sulfur needs to gain 2, but sodium only has 1 to give. So you would have ended up needing 2 different sodiums to come in and each give sulfur 1 of their valence electrons. All right, for the ionic compound formation then, again, either you could have drawn 2 different sodiums or just say like 2 times the sodium. Since they each lost 1 electron, they each need a 1 plus charge. And then you just had your 1 sulfur with now a full octet, and since it gained 2 electrons, a 2 minus charge. All right, so this first part, this is the electron transfer. The second part, this is your ionic compound. All right, the chemical formula then is just how many of each did you use? So we used 2 sodiums, all right, Na2, and 1 sulfur. Remember, if you only use 1 of something, we're not going to put a 1 down here. We just leave it alone. All right, so Na2S should have been your chemical formula. All right, calcium and nitrogen is a little trickier. I'm going to give myself some room and do it over here. Calcium's in group 2A. All right, so it has 2 valence electrons. Nitrogen's in group 5A. So we have 5 valence electrons, meaning it needs to gain 3 in order to look like a noble gas. So calcium right away is going to go ahead and give 2 of its valence electrons to nitrogen. All right, so calcium's happy, but nitrogen is not. Nitrogen still needs 1 more electron. So we're going to need to draw another calcium, again with 2 valence electrons to help it out. All right, 1 of those electrons is going to go to nitrogen, so that nitrogen has a full octet. However, notice that calcium still needs to lose 1 of those electrons. All right, so we need to draw yet another nitrogen. Again, starting out with 5 valence electrons, 5 dots. All right, so calcium can finally get rid of that second electron, but again, now nitrogen still needs 2 more. So this is where we have our final calcium. Again, this is an example of one of those more complicated ones, all right, where you need multiples of both elements. But once that calcium gives nitrogen 2 electrons, now finally everyone looks like a noble gas. Right? The metals, the calciums have all lost their electrons. The nitrogens all have 8. Okay, so that was kind of a long electron transfer, but we're done. All right, this time again, you can draw them all out, but I'm going to choose to use the abbreviation instead. So we're going to say 3 times our calciums, each who lost 2, so a 2 plus charge on both of them. All right. And then I had 2 nitrogens, all right, who now all have a full octet, and they each gained 3 electrons, so they each have a 3 minus charge. And so this is going to be my ionic compound. Again, I could have drawn all 5 of those things out, but I just decided to do the abbreviation instead. All right, when it gets to my chemical formula, again, I want to write how many of each did I use. So for calcium, we always write the metal first, remember. For calcium, I used 3, and for nitrogen, I only used 2. So Ca3N2 would be my chemical formula. All right, hopefully this is getting easier for you, but again, if you have any questions when I get back, definitely we have some time to practice that. Okay, real quick, let's go ahead and review a little bit more. Again, I want to make sure this stuff is good to go when I get back so we don't have to spend a lot of time on it. All right, properties of ionic compounds, these should already be in your notes. All right, we talked about how they have a crystalline structure, meaning basically they're like a solid. They're organized, they have rows, columns. All right, so that'll be important for us to remember when I get back. All right, they're extremely stable because of their ionic bonds. So their ionic bonds are really strong because when a positive is attracted to something negative, that's usually a pretty strong attraction. All right, so their bonds are strong. This leads them to have high melting points because when they have stronger bonds, it's harder to break them, meaning you need more energy, or in other words, a higher temperature in order to make them break their bonds. And finally, we talked about how they're good conductors of electricity. And we talked about how that's because electricity is basically just a flow of electrons from one place to another. And in an ionic compound, we already kind of have a flow of electrons. We have electrons that go from a metal to a nonmetal, or from something that wants to lose electrons to something that wants to gain electrons. And so since we already have that flow established, when they are in water, the flow just goes through the water instead of just through nothing. All right? So that's why we have them as good conductors of electricity when dissolved in water. All right? We're going to go back even further now and review some of those properties of metals. All right? This is all the way back in chapter 6. So this is when we were talking about the periodic table, properties of metals. Remember we said things like they're shiny. That's how we know that it's a metal, because it's shiny. But we talked about some other properties as well. We talked about how one of the main ones was that they were, again, good conductors of heat and electricity. Heat we're not going to talk about as much, but we're definitely going to talk about today, why are they good conductors of electricity? What is it about the way that metals are bonded to each other that makes them good conductors of electricity? All right, so we're going to kind of start moving away from ionic compounds, and we're going to start talking about when metals are just bonded to themselves. All right, so rather than a metal and a non-metal like we had in ionic compounds, now we're going to talk about just metals. So why do those bonds allow them to conduct electricity so well? All right, so kind of be thinking about that as we start talking. All right, we talked about them being malleable and ductile. All right, both of these kind of mean they're durable. They can hold up under pressure. All right, they can change their shape without falling apart. So what about their bonds we talk about today kind of makes them that way? What makes them so strong? All right, if you want to kind of start comparing, all right, this idea that they're malleable and ductile, this makes them different from ionic compounds. All right, it makes them stronger. All right, if you think about a block of salt and slamming it with a hammer, all right, the block of salt's going to fall apart and be what we call brittle. All right, even though they're strong bonds, they're still going to break apart under force. All right, a metal doesn't do that. So what is it that makes them so much stronger and able to kind of handle that pressure? All right, and finally, we talked about how metals are solids. All right, most of them at least. We talked about how mercury is the only one that's a liquid at room temperature, but for the most part, they're solid. All right, which again, like we said before, is just another way of saying they have a crystalline structure. All right, they're organized, there's rows, columns, something like that. All right, so today we're going to finally kind of discuss why that is. So what's the reason? And we're going to use the bonds to kind of help us out. All right, so we're done with ionic bonds for now. We're going to move on to metallic bonds. Okay, so take a second, pause if you need to, so we can kind of run through this. All right, this is kind of a model of what a metallic bond looks like. You can see that for metals, they always want to lose their electrons. So they're always going to be cations, meaning they're positively charged. Positive, or another way of saying that is that they've lost electrons in order to look like a noble gas. Okay? They lose their valence electrons, but in a metal bond, there's nowhere for those electrons to go. They're not going to someone, like a nonmetal in an ionic bond. So instead, they just are kind of free-flowing, all right? And so they just kind of swim throughout this whole structure. You can kind of see those with the green dashes, the green negative charges, all right? And we call them a sea of electrons, okay? Because they kind of just flow throughout the whole structure, all right? So what holds a metal together, it's still a force of attraction, all right? It's still positive being attracted to negative, but this time the positive is the actual metal ions, all right, or the metal cations, okay? And the negative is just all of the valence electrons that they've lost, all right? So they're a lot more mobile. They can flow more, okay? And so the electrons kind of act like a glue that holds the whole thing together, all right, rather than having a negative ion and a positive ion like in an ionic bond. All right, so that's the big difference here between ionic bonds and metallic bonds. Okay, so now that we know what metallic bonds are and how they're formed, all right, between the positive cations of the metal atoms themselves and the free-flowing valence electrons throughout the structure, or sea of electrons, now hopefully we can start explaining some of the properties of metals we learned in Chapter 6. All right, so the first one, and again, remember we said we were going to focus on the electricity part of this, that they're good conductors of electricity, all right? Just like before when we talked about ionic compounds were good conductors because they were able to establish a flow of electrons, all right? And so since electricity is a flow of electrons, all right, from one place to another, all right, the way that a metal is built, the way it's bonded together, has those free-flowing electrons. So a metal bond, or a metal itself, has free-flowing, or another way of saying this would be mobile, right? They can move around electrons, right? And because of this, an electrical current is just going to give them a different way to go, or one direction to go, all right? And so since the electrons are already moving around, it's very easy to create a current from that, all right? These next two are a little trickier, all right? So malleable and ductile, again, this idea that they can hold up under more pressure than an ionic compound could, all right? And so we're going to kind of compare and contrast. So we start out with ionic compounds, all right? They were organized, rows, columns, had that kind of same crystalline structure setup that we see in metals, all right? But for an ionic compound, all right, if we start kind of looking at its organization, it's built up of specifically some ions that are positively charged and some that are negatively charged. And they organize themselves in a way so that they don't repel one another under normal circumstances. So they organize themselves so that they're surrounded by opposite charged ions. All right, so the positives are by negatives, the negatives are by positives, and so on. All right. If, however, you apply some kind of strong force to this structure, all right, what's going to happen is you're going to start seeing these ions getting smushed closer to ions that have the same charge as it. All right, so a positive is going to get closer to a positive, a negative is going to get closer to a negative, and so on. All right, and what do we already know about what happens when you have like charges? All right, our opposite charge is attracted, but our like charges repel one another. All right, so in order to try to stabilize themselves, to stop that from happening, all right, once they start getting too close, you're going to see them kind of break off. So we get these chunks of our ionic compound that break apart, all right, which is why if you smash a block of salt with a hammer, it's going to crumble into a bunch of pieces to try and stabilize itself. It doesn't want to be close to those ions that have the same charge, all right? In a metal, on the other hand, we still see this organization, we still see the rows and columns, and we still are attracted to one another because of opposite charges, but in this case, all of the ions are positively charged because all metals like to lose their valence electrons and become positively charged, all right? What holds them together are the free-flowing valence electrons. So it's still that positives are attracted to negatives, but in this case, the negative charges can move, All right, over here, they couldn't. They were stuck where they were. They couldn't escape. All right, but here, now if I apply a force to this, we're still going to have the positives getting closer to one another, but we have a way to fix that problem. Instead of them repelling each other right away, we can have a bunch of electrons swarm into these areas and kind of provide like a buffer. All right, so we can put all these negative charges as kind of a buffer to keep them glued together. All right, so this idea of, again, having mobile electrons, these electrons that can go wherever they're needed the most, is what's going to make metals stronger, more malleable, and more ductile, able to hold up under more intense stress than an ionic compound could. All right, as far as why are they solids, again, we've kind of already talked about this. This crystalline structure just means they're organized. They have rows, columns, something like that. All right, and this is going to be the metal cations themselves. So the reason they look solid is because the metal ions are in rows, columns, kind of organized in that way. All right, so that one should be an easy one. But hopefully the rest of them are also kind of making sense.